So what I want to do today is to finish the story about the Corey-Vauquelin-Schaeffer bijection and convince you maybe that it's actually a transformation that can be reversed. And after that, I want to start discussing the problem of the scaling limit. Okay, so recall from last time that I have on the left-hand side, I have this family of labeled trees, okay, with a cardinality 3 to the n times the number of plane trees, and the 3 to the n comes from the fact that each edge, if you want, is decorated with +1, -1, or 0. That represents the increment between the two vertices adjacent, incident to that edge. And then I had to add this little decoration that will serve later for the orientation of the root. We'll come back to that. And I claim that, actually I only described so far that side of the construction, going from this family to the set of quadrangulations that are also pointed and rooted with n faces. And here is again how the construction goes. So maybe I will not draw a full example. So maybe actually let me stick to my color code that I used yesterday. So I think the tree was in red. Okay, so let's say the root has to have label 0, maybe 1, 0, -1, and so on. Something like this. And you remember that in order to go from this label tree to a quadrangulation, starting from any corner, so let's, for instance, take this corner, okay, let's call it C maybe, I have to link it to the next available corner with strictly smaller label. Okay? So in this case, -1. And if it turns out that the corner I'm starting from has minimal label overall, okay, then I just link it to an extra vertex called V star, and that carries a label which is what it should be, right? The minimum label -1. So in this case, it's -2. And that was the construction. When I add all these arcs, so actually I didn't give a name to that, but let me call that an arc. So we draw an arc from a corner to the successor. And the claim is that the white graph that I obtained, so the graph made only of the arcs, forgetting the edges of the tree, is a quadrangulation. Okay? So let me actually prove this fact. So claim it is possible to draw the arcs in a non-crossing way. So that the arcs form an embedded graph. Okay? And well, this fact is fairly elementary as soon as you remember that a tree, you can see a tree itself, it can be seen as a map, okay? But a map with only one face, okay? Because it's a graph embedded in the plane and it has no cycles. So we really want to view the tree so maybe we started from a tree T with labels L, and we'll end up with a quadrangulation Q. We view the tree as a polygon of degree 2n, where n is the number of edges in the tree, with edges identified in pairs So how do you do that? Well, you imagine that this blackboard is made of a sheet of paper, and you cut along the edges of the tree. So that means that you really duplicate all the edges of the tree in this way, and you really open up the tree. So the polygon is now this region, if you like. Okay, and then you unfold it. So you will obtain something like that. Okay, so maybe in this case you will really need 14 vertices or something like that. And you see, when you go now along this polygon, you will have some identification. So let's imagine that this should really correspond to the root of the tree. Okay, so it means that the next two edges that I'm encountering should be identified. So it means that these two edges really have to be glued together. And then the next, so these two edges will be identified together, and so on and so forth. So maybe I will not do it for the whole tree because I might make a mistake. But you really have if you like, a non-crossing diagram of identifications within the tree, within the polygon. Okay, so something like this. And then, of course, some of the vertices of the tree will be duplicated on this polygon. So for instance, these two vertices really are the same. But I can just put on their labels there. So this one has label 0, it's the root. Then the next one has label 1. Then I am back at vertex label 0, and so on and so forth. So the next one will be 0, -1, and so on and so forth. Okay? And you see that, so again, you should imagine that all these identifications, this is not really all these identifications give only the embedding of the tree. Okay? So what's available for me to draw the arcs is really the outside of this polygon. And so the fact that you can draw the arcs in a non-crossing fashion just means that it is not possible, so maybe I should use the same color again, it is not possible to find two corners, or actually four corners, say E1, E2, E3, E4, such that the successor of E1 is E3, and the successor of E2 is E4. Okay, if I can show that it's not possible to get this situation, then it means that I can indeed draw the arcs in a non-crossing fashion. Okay, so I want to show that there does not exist E1, E2, E3, E4, such that this situation arises. Okay, but then it's very simple to see that it's not possible because, so let's call L the label of E1. That means that E3 has label L-1, and also it must be the first available corner in this little arc of the polygon with this label. So it means that all the labels here should have label bigger than or equal to L up to E3. Okay. Now let's call L prime the label of this vertex. Okay. So in particular, L prime is bigger than L, and then this one has label L prime -1, and it's also the first label on this interval with the label L prime -1. So all the others have labels bigger than L prime, and you obviously get a contradiction, okay? Because L -1 is in fact smaller than L prime. Okay, L -1 is, L prime is bigger than L, so it's strictly bigger than L -1. Okay, so this cannot happen. Okay? So, so I know that at least the graph of arcs is an embedded graph. Now, of course, it's also connected. Okay? So let me call Q the graph whose edge set is given by the arcs. Okay. Of course, Q is also connected. Okay, because from every vertex V in the tree, I can start a chain of arcs from any corner incident to V. Okay, so you start from C, then you go to the successor of C, and you go to the successor of C, and so on. And every time the label is, diminishes by 1. So after some time, necessarily you must stop and arrive at the vertex V star. Okay, and that gives you an explicit chain from the vertex V, okay, to the vertex V star. Okay, so I want to call that a successor chain. Okay, and so therefore the graph is connected because every vertex is connected to V star. Okay, so this implies that Q is a map, and it's really a map on the sphere. I didn't discuss the surface on which it is drawn, but it's on the plane, right? And the plane, you can see it on the sphere by just adding a point at infinity. Okay, so it's a graph drawn. It's the reason why you call maps drawn on S2 as a plane maps, rather than spherical maps. So that's the first claim. Okay. Now the second claim is that Q is a quadrangulation with n faces. And what's the reason for that? It's also fairly simple. So let's look at a given edge of the tree. Okay, so an edge in the tree has one of the two following forms. So this is an edge of T is of either of the two following forms. So either it links two vertices with labels that differ by 1, okay, or it links two vertices of the same label. Okay. Now let's look at the first situation. Okay. So in this case, well, certainly the last corner around this vertex before this edge has to be linked to this guy by an arc. Okay, because well, the next available vertex with label L plus 1 minus 1 must be this one. There is nothing in between. Okay? And let's look at the other side. Well, first of all, this corner, the last corner before coming back to that edge, it has to be linked to a vertex with label L minus 1. Okay? Okay, so this is, if you like, this is the edge, the oriented edge E, or the corner incident here, and this is the successor of this corner, and now this is C prime, and this is the successor of C prime. Okay. But now let's look at this L plus 1. Okay, so it's incident to another corner C double prime, and its successor must be a vertex with a label L. But necessarily, this vertex with label L must come before this one. Okay, because it's the first vertex with smaller label than L plus 1 coming after this corner in the contour exploration. Okay, so necessarily the successor of this successor must also be the first available vertex, which is this one. Okay, so this successor of C prime must be the same as the successor of C double prime. Okay, and as you see, what I've drawn here is really a quadrangle that entirely swallows the edge of the tree I started from. Okay, so this is a face of degree 4. Okay? And here the situation is even simpler, so I'm going to go a little faster. So if I look at this corner and that corner, then they both must have the same successor, okay, which is a vertex of label L-1. And so this is S of C equals F of C prime. And the same must be true on the other side. Okay. And here again, I find a face of degree 4 that includes one of the edges of the tree. Okay. And yes.
How do you know you have at least 2 corners from the L+1 vertex? If it's a
which one? This one?
Yeah, if it's a leaf, do you have?
Yeah, that's correct. In this case, it means that C double prime is equal to C, and that's fine. I didn't say that these 2 vertices are different. Okay? And in fact, it's possible that they are the same. That's precisely what happens when you have a quadrangle of this form. Okay? And all the same here, actually. You know, these 2 vertices can be, in fact, the same. And that will happen when you have a quadrangle. Let's see if I can get that right. Okay. Okay. So you see that every edge of T is included in a face of Q with degree 4, and by construction, you know, by construction, these faces they do not contain any other edge. Okay, it's fairly simply to see. Okay, so therefore, Q has at least n faces of degree 4. Okay. Now I claim that all the faces of Q are there. Okay, and that will conclude the proof. And in order to show that, let's use Euler's formula again. Okay, so now note that Q has well 2n arcs, 2n edges actually. Okay, so it's 1 for every corner of T. And what is a corner of T? So let me maybe draw a picture here. So a corner, I said, is a little angular sector around the vertex of T, but you can also associate every corner with one oriented edge of the tree. Okay, the corners of T are the same as oriented edge of T. Okay, so if you fix an oriented edge of T, you just look at the angular sector that arrives on the left of this oriented edge. And an oriented edge of T, I know that T has n edges, so it has 2n oriented edges. Okay. Okay. So Q has 2n edges, and it also has n plus 2 vertices. Why is that? Well, it has the n plus 1 vertices of T. Remember that a tree with n edges has n plus 1 vertices plus V star. Okay? And the list of vertices is all there. Okay? So, by the Euler formula, we know that the number of vertices of Q, the number of faces of Q is equal to 2 plus the number of edges minus the number of faces. Oh, sorry, the number of vertices again. Okay, and that's n plus 2 minus n plus 2. No, 2n plus 2 minus n plus 2, and that's n. Okay, and so we found all of them. Okay. Okay, so before I move further, I want to emphasize again that the quadrangulation I get from this construction seemingly has more structure than only the quadrangulation. It also has the labels that it inherits from the tree. Okay, so let's give the interpretation of the labels. Okay, so the map Q inherits a label function, labeling function, let's say L from the set of vertices of Q to Z from that defined on T. And why is that? Well, again, the set of vertices of Q is nothing but the set of vertices of T plus the distinguished vertex V star. And remember that all the vertices of T have a label by definition. And V star, I gave it a label. You know, L of V star, by definition, is the mean of L on all the vertices of tree minus 1. Okay. And the claim, so fact or say a proposition, is that for every V vertex of Q, the label, okay, the label of V is essentially the distance, the graph distance in Q between V and V star. And that's true, of course, the labels, they can be positive or negative. So I have to shift the labels to make them all positive, or at least non-negative. Okay, and I just shift them by the minimum label, so the label of V star. Okay, so the same as L of V minus minimum of L on T plus 1. And that's really the key property of the Schaeffer bijection that's going to allow us to deal with scaling limits later on. Okay, because not only have I given you a way to construct a quadrangulation, so if you want to consider a quadrangulation uniformly at random, well, it's very simple. You start by taking a tree at random, a label tree at random, and you apply the Schaeffer bijection. So it's since it's well known actually how to sample trees, it's very simple algorithmically. This actually gives a way to sample quadrangulations. And in fact, people who do computer simulations of random maps usually use this kind of things. It's really the simplest way to sample a random map. And but not only have I given a way to sample the map, I've also given a formula for a large family of distances within the map. Okay. Okay, so let's, you know, the proof of this proposition is really not very difficult. You know, so let's take V maybe in the set of vertices of T. Okay, so of course for V star there is nothing to prove, right? V star is at distance 0 from itself. So let's take a vertex in the tree. Well, note that the successor chain, maybe the successor chains from V to V star, well, has exactly the length that I'm claiming, okay? Because along the successor, I decrease labels by 1. So starting from the label of V, I have to make as many steps as L of V minus L of V star to reach V star. Okay, so the successor chains from V to V star have length L of V minus L of V star, and that means that dq of V to V star must be less than that. Okay, the minimal path must be shorter than the path that I've just produced. Okay. But conversely, the labels along any path in Q from V to V star, vary by 1 in absolute value at every step. And so necessarily, if you want to go from a vertex with label L to a vertex of label L prime, you need at least L minus L prime steps, absolute value of L minus L prime steps. Okay, so the length must be bigger than L of V minus L of V star. Okay, so more generally, actually, the same proof says that, in fact, the distance between V and V prime certainly is bigger than L of V minus L of V prime for every V prime by the same proof. Okay. So it's of course, this lower bound is not very good because if V and V prime can be very far away in the map, but just be at the same distance seen from V star. In this case, this lower bound will tell you nothing. Okay, but still, it's already something. Okay. Okay, now I want to spend maybe 10 minutes on the converse construction, because I think it gives if it's the first time you see this bijection, and I know a significant proportion of the audience has already seen it before, but of course it's a nice construction, but how did they find it, right? It's a kind of mysterious construction, why it works. And what I'm going to do is to try at least to give a, someone like Gilles Schaeffer would be more entitled to say how you actually produce these bijections, but at least I'm going to try to give you a little bit of geometric intuition about how it works. Okay, so a word on the converse construction. We are not going to need it, by the way, but I think it's an interesting story. So in fact, here I'm going to start from any map, okay, any plane map. So some of the faces can be triangles, pentagons, whatever. Can have maybe self loops. Okay, let me maybe add a couple of faces, something like that. Okay, so remember now I want to start from a map which is pointed, and what I want to get is a tree. Okay, so I point the map at a given vertex. Okay, this is V star, and this is a pointed map. And now I want to imagine this map as being a road network. Okay, so you imagine that these edges, they are in fact highways. Okay, and these highways connect the different cities that stand at the vertices. And there is a reason why I put circles around the vertices, not only to have the place to write the labels in them, but I really want to consider now these edges as part of the graph. I augment, if you like, a little bit the graph. And I want to consider these as ring roads going around the different cities. And now this is the origin city from where all the cars are built. So it's Detroit, if you like. Okay? And from Detroit, you have the cars are going to go in all America. Okay? There are also other stories about call that snail operations, in France with people blocking the roads. But okay, let's stick to the American image. Okay, so all the cars here, they just completely invade the ring road around Detroit, and then they take the highway. So you should imagine that all the highways have the same length, which is 1. Okay, so at time 1, what happens is that the cars will have arrived at the same time in all the neighboring cities. Okay, and you should imagine that the ring roads, they have a negligible size compared to the size of the highways. Okay, so instantly the car starts going around the ring roads, but they must yield priority. Okay, after they arrive at this last exit, they cannot go further because they would encounter their own flow. So they have somehow they cannot go that way. It's forbidden. Okay. So by the way, it's the American convention, not the UK one. But algorithmically, in fact, the UK one is better. But I will explain maybe if I have time, or for office hours maybe. Okay. So at time 1, the cars are there and they have invaded the ring roads like this. Okay. Now what happens at time 2? So here, no problem. They arrive here. They arrive here. And now something funny starts happening. Okay, because you see that in this highway, for instance, the two flow of cars, where they actually meet in the middle. Okay, and these are one-way highways. It doesn't exist, but they have to stop. Okay, and they stop actually at time 3/2. Okay, and here it's the same. Okay, they try to go along this road, but they meet in the middle at time 3/2. And now you see, for instance, on all these on this ring road, everything is blocked. Okay, each flow of car blocks the other one, and on this one, only this one can continue. This one is blocked by the one on its right, and here only this flow of car can continue. And then what happens is that this flow of cars meet in the middle of the edge at time 5/2, and at that time everything is invaded. Okay, so nothing happens anymore. So what do I get in the end? Okay, so what do I get is a red tree on the augmented map, where a vertex incident to 4 edges is replaced by this ring road. Okay. Why is it a tree? Well, by construction. Okay, maybe here I have one cycle. So let's imagine that this is only one vertex. Okay, but otherwise, I constructed a graph without cycles, just by definition. I didn't allow, the edges of the graph to produce cycles. And it's also a tree that covers all the vertices of the augmented graph. So what I can do is construct, if you like, the dual tree on the dual map. So what I do is, in each face, I add a point, And what I'm going to do is, whenever I see a white edge in what's remaining, I'm going to cross it with a green edge. Okay, so here, this, if you like, this vertex 1 is connected through that white edge to this green point. This white edge is also connected there. This white edge is connected there, 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 so on. Let's see. And then also at the points where the flow of cars met, I also want to leave some space. Okay, so I allow a crossing through these places. And you know, by construction, what I obtain is a green tree. So not really a dual tree because I had also to augment a little bit the graph here. And I want to mark the passage points through these middle of edges by little flags, okay, in order to distinguish them. Okay. So it's a, you know, it's a tree which has three different kinds of vertices. Some vertices that are labeled, some flags that are labeled with, you know, even integers divided by 2, and some unlabeled vertices, you know, in the middle of the faces. Okay, and there are some rules. Okay, for instance, a flag has to connect necessarily two vertices of that kind. Okay, and those vertices can be either connected to flags or to labeled vertices, round vertices. Okay. The claim is that this, when applied to a quadrangulation, gives the tree I started from. Okay, and we'll see how it goes. So by the way, so this construction, starting from a general map and getting one of these decorated trees, is called the Boutier Di Francesco and Gitter bijection or construction. So from a map, you get what they call the labeled mobile. And they call that mobile because of the resemblance with the art pieces by Calder, you know, the mobiles. Well. And yes.
Repeat just briefly, just to repeat, basically, how do you get the green tree? So you start with the dual vertices and then
yes.
Connections?
Yes, so you draw the connections. So along every ring road, okay, you will have some parts that are colored red and some parts that are not colored. Okay, so maybe you will have 3 parts colored red like this. Okay, so it means that, of course, all the edges after some point are colored red. So you get a picture like this. And what you do is you connect the white parts, the parts that are not covered, to the dual vertices within the incident faces. Okay? Is that clear? So maybe before I comment further on that, you can also see how the converse construction goes from that green tree, okay, to the red tree. So maybe it's going to be a bit hard to see, but let's look, for instance, at this vertex, okay? So this vertex in the green tree is incident to, for instance, this corner, and it's connected to that other vertex. And you can check that this other vertex is precisely the next vertex with smaller label that you encounter when you go around the green tree. Okay, you have a label 2, go around the green tree, and you encounter this one labeled 1. So you connect it to it by you connect the 2 to the 1 by an arc. And the same is true of for other vertices. In fact, for instance, starting from this corner of the 1, you go around the green tree like this, And oh, okay, that doesn't work. That's bad. Oh yeah, no, it works, of course. So from this corner, you go around. Well, this one has this one has minimum label. That's label 1, so it has to be connected to the 0, okay, by this arc. Okay, and so let's take another example. For instance, this 2 here is connected to the next available one, okay, which is this guy. Okay, and this 2 has actually another corner here, which, when I go around the tree, is indeed the next available vertex with a smaller label. Okay. Okay, so now how does it work in the case of quadrangulations? Well, for quadrangulations, in fact, the right thing to do is to look at the faces of the quadrangulation. Okay, so the faces, they will be labeled by the distances to V star. So let's, okay, so of course the labels that appear here are the distances to V star just by construction. Okay, so for quadrangulation, there are only two possibilities. You know, if this is the closest vertex to V star, then the two neighbors must have a label which is bigger, because, as I said, for quadrangulations, there are no cycles with with odd length. Okay, quadrangulations are bipartite, so it means that you know, if two vertices in the quadrangulation at the same distance to V star, it means that I could construct a path with length 2L plus 1, a cycle, if you like, with length 2L plus 1, and that would not be possible. Okay, so this cannot happen. So necessarily, I have only two possibilities, which are given by these. Okay, and now let's look at what happens. So from this vertex, there must be some incoming flow of cars, which goes through that ring road. Okay, so certainly, since these have bigger labels, the cars cannot go from that side. Okay, so this ring road has to be closed at least up to this point, and then it must spread up to L plus 1 in these two ways. Okay, and for the same reason, that part of the ring road must be closed, but that one has to be left free. Okay, then it has to spread there, and there it has to be closed as well. Okay, so the situation must necessarily be of this type. So if you are not convinced, it's a good exercise to see it at home, and therefore the situation in these quadrangles must be of this form. And in those quadrangles, the situation is more symmetric. So the road must be closed on that side, and must be closed here on the other side, and the two others must be free. So it means that the situation must be like that. Okay. And now what do you get? You obtain that the green tree that you obtained from the Boutier-Di Francesco-Gitter construction, well, has only two types of configurations around the green vertices. So get either configuration with, say, L plus 1, L plus 2, or LL, or actually L plus 1, L plus 1. Okay? And here you cannot tell actually what is the vertex which is closest to the root. Okay? It would be upside down. So you see that you can in fact forget these vertices, and you exactly obtain the situation where you have L plus 1, L minus 1, or L plus 0. Okay? Okay, so the possible configurations, in fact, are there, and you see that the Boutier-Di Francesco-Gitter construction, in this situation, it yields a plane tree plus labels, which is an element of Tn. Okay? Now, okay, so of course, this construction is a bit complicated. Also, I chose to give you the most general construction, which is even more complicated. But at this point, I want just to explain that, in fact, you almost see here that you exactly get the converse construction of what we obtained before, because these two configurations here with well, actually, I chose the wrong color code, so that's too bad. But you know, this quadrangle here, swallowing one edge of the tree, is exactly the quadrangle that was on this blackboard here on the left, okay, with colors that have changed a little bit. And this one is exactly the one that stands on the right. Okay, so on this picture, it's actually quite intuitive that what you have done is exactly the converse of the construction over there. Or actually, it goes the other way around, if you like. Starting from these two kinds of faces, well, you immediately see that the red edges associated with these faces are the green edges that are defined on this blackboard. So with this construction, at least I showed you something, which is that this construction is the inverse on the left of the previous construction. Okay, if you apply the Corey-Vauquelin-Schaeffer construction starting from the tree, get the quadrangulation, and go back to the tree using that, you get the tree you started from. Okay, so what's missing in the proof is the fact that it's also an inverse to the right, and it's slightly more complicated. Okay. Okay, so actually I should use this blackboard. So comparing let's say this diagram and this diagram, actually maybe it should be the other way around, comparing a star and a double star, we get that the Boutier, Di Francesco, Guiter, you know, I'm not really respecting what's really applied to the Corey-Vauquelin-Schaeffer bijection of TL is equal to TL. Okay? If I call BDG that construction there, and Corey-Vauquelin-Schaeffer, the bijection, actually it's always on the blackboard. It's nice. Okay? So again, so why did I spend actually more than 10 minutes describing this this construction? I think it's because it tells really something about how these bijections are built. So what you do is, again, if you view the map as a kind of abstract metric space, you start the geodesics from a given point in that metric space, and you look at how the geodesics actually can meet at different points of the, actually how certain points of the map can be reached by two different geodesics. Okay? And what we did is that whenever that happened, we gave a priority rule for one of the geodesics to be allowed to continue while the other one was stopping somehow. Okay? And essentially when a point can be reached by three different, you know, by several different geodesics, or it could be even only one, and nothing can continue, then we completely stop. Okay? And whenever that happened, well, we had the dual tree that was going in between these four geodesics. So this construction is actually analog to what is called the cut locus of Riemannian surfaces, well, actually Riemannian manifolds, which are the set of points, okay, that are reachable by distinct geodesics. Okay, so in a general Riemannian manifold, starting from a given point, you can define the exponential map that draws all the possible geodesics starting from that point. Okay, essentially, you just give a direction starting from that point, and for some time, all the geodesics will be completely disjoint, up to a certain point, which is called the injectivity radius, where the geodesics start meeting. So at this point, the exponential map is not injective anymore. And if you look at the collection of points where geodesics fail to be unique, you actually obtain a tree, okay, which is drawn on the surface, or an object which has the form of a tree. And the idea is that here, this Corey-Vauquelin-Scheffer tree is really a discrete analog of this cut locus. Okay, and a very beautiful result of Le Gall, which I hope I will have time to explain to you later, says that when we will pass to the limit, we will see that the continuum analog of this tree can also be interpreted as the cut locus of the Brownian map. Okay, so I hope I will have time to explain that. Any questions so far? Okay, so in the remaining 7 minutes, I want to start the exploration of scaling limits of maps. Okay, and so essentially the combinatorial part of the lecture is finished here, and now I want to do probability. Take random trees and random maps. Okay, so before that, so where do we stand at this moment? Maybe I will use a blackboard over there. So now we know that to sample a uniform random quadrangulation, say Qn, so we can take the uniform random element, say Tn ln in Tn, okay, then apply the CVS bijection, the Corey-Vauquelin-Scheffer bijection, and this bijection, this construction actually is going to give me not only a quadrangulation but the distinguished vertex V star, okay, but the marginal law, if I forget the vertex V star, Qn will be uniform, because for every Qn, there are the same number of choices for V star. Okay, so since the choice of V star is unbiased, so there are n plus 2 choices, whatever the value of Qn. This means that Qn must be uniform in the set of unpointed quadrangulations, okay? And moreover, V star is uniform in the set of vertices of Qn conditionally given Qn. Okay? Yes? Yeah, they are rooted. So I didn't emphasize a lot the way in which you route Qn. And if you remember, it actually depended on an extra data. You know, I also needed to fix a sign in order to give the orientation of the route. So if you like, you take epsilon plus or minus 1, but it really doesn't matter. Okay? So now the strategy, so remember that we want to understand the scaling limit of random maps. Okay, so we want to understand Qn. So now we are in good shape because we know how to describe the graph distances, or at least some graph distances in Qn, using the labels of the tree here. And now what I want to do, now and in the next lecture, is to explain how you can first take scaling limits for random trees, and then hope to be able to apply a continuum version of the Corey-Vauquelin-Schaeffer bijection. Okay, so the plan now is first to take scaling limits of labeled trees, and to define a continuum Corey-Vauquelin-Schaeffer bijection and apply it to the scaling limit. So that's the rough plan for what's coming. Okay, so let me just start with the part on scaling limits of labeled trees. Okay, and in fact, before looking at labeled trees, I'm just going to look at trees. So let Tn be a uniform random plane tree with n edges. Okay. And we want to understand the structure of this tree as n goes to infinity. So in fact, it can be conveniently encoded by a random path called the contour function. Okay. So what is the contour function? Well, starting from any tree, actually it's important that these trees are plane trees, that they are embedded in the plane. Now I can consider the walk that goes along the tree in clockwise order, and at every integer time, every time I meet a vertex, I record what was its height, its distance to the root. Okay, so here, starting from there, I get a walk that does something like that. It goes up, then down, then up again, up, down, up, and so on. Okay. Okay. So if you prefer, let V0 be the root, V1, V2, and so on. The clockwise exploration of vertices. So every vertex is encountered as many times as its degree, and set contour process at time I to be the height, so the graph distance in the tree T. So maybe this was a tree T. The graph distance from V0 to Vi. And you extend it into a broken line path. Okay, I'm almost finished. So obviously, it's also possible to invert this construction, starting from any broken line path which is non-negative and starts and ends at 0 after 2n steps. Okay, 2n, n is the number of edges. you can also go back. Okay, and it's good that you think a little bit about how you can actually do that. Okay, so you get that the trees with n edges are in bijection with walks, if you like, simple random walk paths that are non-negative on 0 to n, and start and end at 0. Okay, and this I want to call that an excursion of a random walk of length 2n. So the idea is that now a tree is coded by a simple random walk path, only with a little conditioning. But then it's natural to get, to guess how this path should rescale as n goes to infinity, and this should be done by a diffusive rescaling. So if you rescale in time by the length of the path, which is 2n, and rescale in space by the square root, okay, so it's really the Gaussian or diffusive scaling, then this converges in distribution as n goes to infinity to a limiting process, which is, it's called the normalized Brownian excursion. It's Brownian motion conditioned on b restricted to 0, 1, to be non-negative, and b1 equal to 0. It's a normalized Brownian excursion. So of course, this conditioning really doesn't make sense. As you know, a Brownian motion is takes instantly negative values. So this, for many reasons, this conditioning event is very singular. But nevertheless, the take-home message here is that this contour process really looks like a random walk. So it's normal that the limit should have some kind of Brownian flavor to it. And next time, I will explain this result and how you can turn it into a convergence of the trees themselves. And that's all for today. Thank you. Questions? So are we continuing right now with
Yeah, I think so.